Hi, my name is Akifumi Takahashi and I'm presenting a work I did together with my colleague Jas Brooks, my PhD advisor Hiroyuki Kajimoto from University of Electrocommunications Tokyo, and my internship advisor Pedro Lopes from the University of Chicago. The field of haptics has come a long way in the last decades. We explore haptics for touching objects in virtual reality, learning new physical tasks, and much more. Here we see an exoskeleton glove that can move the user's finger involuntarily. Unfortunately, it uses large motors that are not trivial to miniaturize, so these devices are very limited in their applications to wearable or everyday situations. So in order to build more mobile applications, researchers in HCI in the past decade have been exploring another technique called electrical muscle stimulations, or EMS for short. And you can see here it's very small because it just applies electrodes to the body. Now using EMS, people have been building all sorts of interactive systems. For instance, this system, the possessed hand, simulates fingers to play some simple note combination with this instrument. This system, Affordance++, can make you shake a spray can so you learn how to manipulate an object that you've never seen before. This one, called Muscle Porter, controls your wrist and port for you. And this one can move your wrist to tap to a beat so you learn some beat patterns. But when you zoom out, you see what exactly is the quality of the actuation provided by these systems. You see all these systems, or many others found in the HCA community, actuate only large muscles like legs, arms, or the wrist, with very coarse movements like wrist up and down. And in fact, the possessed hand, which is proposed about 10 years ago, is still the most precise system we got. So what is preventing EMS from getting better? So here I'm gonna move the index finger using EMS. So the first joint, which is called the MCP, is the joint I was targeting, but the finger also moved around another joint of the same finger, and the pinky also started to move. So actuating by placing electrodes on the forearm to control finger muscles suffer from the lack of dexterity. Alright, so why does this happen? As you can see, all the finger muscles anchor at this bone, and so they are very densely packed. When you apply the electrodes on the forearm, it's natural that the current goes through adjacent muscles or ones at a different depths. So our approach is to move the electrodes on the back of the hand. So we can precisely target the first joint of the finger without moving the others. Now to validate this, we ran a study comparing to the standard approach of just putting the electrodes on the forearm. We found that the finger moves more independently. There's less unwanted movement. Our approach is more rotation invariant, so you can see that if I turn my wrist, it still works well. And turns out it takes less time to calibrate. So using our back of the hand actuation, you can build new applications at a new level of dexterity. Let me show you a few applications we made. Here you see a user doing a simple chord that presses all strings with one finger. And you see a user doing a special drum stroke that requires a very fine movement with one single finger. And you see a user learning how to play a simple melody. Now, back of the hand is without limitations. As I mentioned, you can only move that first joint, so there's still a lot of way to do for us to unleash full dexterity of EMS. We need to move 2 more joints of the finger, and we need to work also in other direction, because so far we only flex the finger down. But we also need to unleash dexterity of the extending direction. So I'm really excited to see what you all will build with the back of the hand stimulation. Thanks for listening.